All right, so looking at this equation, what is different about this versus the other ones? Okay, do you catch the idea that there's a 3 theta? Do you see that? Okay, so guess what that means? Well, at some point we will, right? But this means it's different than the other examples we've seen. So there's not going to be a straightforward identity that we can convert this to, but there is something we can do about that. One thing I just want to remind us of, in an earlier lesson, we actually derived the triple angle for cosine, I think. And there was a proof that had the triple angle of sine in it. So one option is you could spend the 10 minutes it takes to derive a formula for the triple angle, but that's not actually how we're going to go with this. We're going to go a slightly different approach. Because if the 3 theta wasn't there, it just was 2 sine of some angle minus 1, I would know what to do, right? It's that 3 that's making this sort of challenging. So let's kind of have a quick conversation about something then. So if theta lives in 0 to 2 pi, where does 3 theta? What would be the domain of 3 theta? 0 to 6 pi. Okay. Now, what's so special about 2 pi to 6 pi? Like, what does that physically mean we're doing? It means we're looking at the unit circle and we're going around the unit circle 3 times, right? Okay. So what I'm going to do is I'm going to temporarily make a new angle. And I'm going to call it beta. Why? Because I can. Because I had to call it something. I like beta because we don't use beta that much in problems, but it's another name for angles that we could go with. And so what I'm going to do is I'm going to set up this same equation in terms of beta, keeping in mind that beta goes around the unit circle 3 times, and then I'll come back in and reconcile this for theta. But if I rewrite this, I get 2 sine of beta minus 1 equals 0. Okay, well that's something we know how to solve. It's kind of like doing a U substitution, yeah. All right, so sine of beta, what would sine of beta equal? 1/2. Okay, so we're actually familiar with that one. We've seen that one a couple of times today. It's positive in the first and the second. We're looking at that angle, and so what angle, at least one time around the unit circle, what angle would we be looking at? Okay, pi 6 and 5 pi 6, right? Okay, comma. Because I want to remind you, we said we're going to go around the unit circle how many times? 3 times, right? So that's the first time around I get pi 6 and 5 pi 6. How do I get the second time around? How do I get the coterminal angle with pi 6? These are all fabulous numbers. None of them actually represents what we go around. So if you go around 1 time, how many radians is 1 time? 2 pi. Okay, so I want to take pi 6 and I want to add 2 pi. So let's think a little bit harder about this. What fraction was equivalent to 2 pi? How about 12 pi over 6? How do I get the 12? Just right, 2 times 6. Right? So 12 divided by 6 is 2, right? Okay. As opposed to some of the other numbers that were yelled at me. All right, so pi 6 plus 12 pi 6 is what? 13 pi 6. Okay, so there's another answer. Let's do the 5 pi 6 plus 2 pi. All right, so that's 5 pi 6 plus 12 pi 6. All right, so if I add that together, what do I get? 17 pi over 6. Okay. Now I'm going to sort of have us look at our numbers for just a second. Do you notice any pattern? Where'd I get the, that is a 5. Here, I'll make it a little prettier. Is that a little bit better? Now it looks like a 5? Okay. It's a 5. It's still a 5. All right, take a look at our 4 numbers. Do you notice any interesting pattern? So when I go from like pi 6 to 13 pi 6, what do I do? Notice how I just added 12, right? 5 pi to 17 pi, what do I do? Add 12. So I could go back in and I could do another add 2 pi, or I could just go, hey, let's just add 12 pi to the top. So if I take 13 pi over 6 and add 12, what do I get? 25 pi over 6. And if I add 17 pi plus 12, I get 29 pi over 6. Right? So far, so good. Okay. Now, that's great. That's all beta, though. I want theta. Okay. So what I have to do then, I'm going to come down here. I have, I'm going to go back in and substitute in 3 theta for pi over 6. And 3 theta equals 5 pi over 6. Now, I'm just going to pause right there because I've got 6 of these answers, so I can go back in and 3 pi equals 13 pi over 6, 3 pi equals 17 pi over 6. But I claim, once we figure out what to do with the 3, that we can just jump through and write the answer. Once we understand what the 3 does for us, then modifying those 6 fractions is going to be pretty quick. So how do I get rid of the 3? Divide by 3. Okay. So if I take both sides and divide by 3, all right, so I get theta equals, well, what's pi over 6 divided by 3? Ooh, I heard 2 answers, the 2 directions that a lot of students go. So I heard them in the multiply thing and the divide thing. All right, so let's kind of remind ourselves of the rule. So if I am dividing by a fraction, then I'm going to multiply by its reciprocal. So it's pi over 18. Okay. So guess what's going to happen to all of our denominators? They're all going to become 18 for the exact same reason, dividing by 3 every time. So I can very quickly come in here and say, well, theta then is pi over 18, 5 pi over 18, 13 pi over 18, 17 pi over 18, 25 pi over 18, and 29 pi over 18. Okay. Kind of make sure everybody's on board with this, because we're actually not done, because we actually didn't read the question to see what we're answering. But we have answers. Anybody lost, confused about how we got to this point? Or I guess what would, in order to get here, what do we have to remember in order to get this right? Okay, so we have to remember our fraction rules. Make sure we get that one right. Okay, so once we've done sort of an angle substitution, remember we're solving for theta, not beta. Okay, effort. I like that. We have to actually try to get it right. Okay. All right, so let me kind of go up here. So the question actually has 2 parts. It said find the solutions to the equation, and that is talking general case. And then find the solutions between 0 and 2 pi. So I'm curious if we actually answered that. Let's kind of go back down here. If I want to look at between 0 and 2 pi. So did I get the answers between 0 and 2 pi? How do you know I don't have more? Okay, so if I think about it for a second, 2 pi is 36 pi over 18. right? And so if I look at my list of angles, I've got 29 pi. So actually this fraction right here is less than 2 pi. What happens if I add another 12? I pass, so if I add 12 to the 25, I get 37, and that's bigger than 36. So I've got all the angles between 0 and 2 pi. Okay, so we actually did answer one of the questions. The other question is the general case. So I'm going to come back up here. Well, what do you notice about find all solutions? Let's come down here. What do we notice is like going from one to the other? We kind of had this conversation, but if I go from pi over 18 to 13 pi over 18 and 13 pi over 25 pi, what am I doing? I'm adding 12 pi over 18, right? So I'm adding some multiple of that. So in general, so if I wanted to figure out an infinite number of these things, I would say pi over 18 plus 12k pi over 18 would give me an infinite number of these angles. And then what would the other form look like? 5 pi over 18 plus 12k pi over 18. Okay, so that would give me a general case. So you tell me how many answers you want, and I'll plug a k in and figure out the angle that goes with that. All right, any question on that?
So the number in front of the k will just always change according to the difference?
Well, the general case means all of my answers are going to look like this pattern. I'm not saying how many, like unless you tell me how many answers you physically want me to generate, there's no sense for me to just get rid of the k. I'm just going to leave the k there. So all of my answers are either going to look like pi 18ths plus some multiple of 12 pi over 18, or they're going to look like 5 pi over 18 plus some multiple of 12 pi over 18. So again, the general case is just a statement of, in general, what do I see with my numbers? Okay. All right, anything else on this one? What is that? Okay. So looking at this equation, how is this different than the other ones we've seen today? It's actually not the square root that makes it different. It's the theta over 2, right? We actually, the square root of 3 is one of our common unit circle values. We actually have a tangent value we can look up that'll help us figure that out. The problem is the theta over 2. And the theta over 2, or the half angle, is the same problem as that 3 theta from the last example. So we're going to redefine a new variable, set up an equation in terms of the new variable, find out, go around the unit circle as many times as it wants us to, and then substitute it back in. So kind of do the same approach we did last time.
Why can't we just use like the half angle formula?
You can. And tangent of theta over 2 is actually not bad. Although I think it's got 2 different trig functions in it. So then we'd have to reconcile. So we can do the substitution approach, or if we want to try to convert it to the half angle formula, then we'd have to rewrite the equation. And I think at some point we'd have to square both sides. And then we'd have to go back and make a list of solutions and then go back and check each. You see how this is getting a little bit longer and longer? So half angle, I think, is a reasonable one to maybe want to look at doing that with. But if you do the substitution angle approach, there's just one method, and it doesn't matter if it says theta over 2 or 3 theta or 4 theta. You're always going to get it right. That's how I would go about saying that. Okay, so come back down here. They are, for whatever reason, telling us that theta lives between 0 and 4 pi. Okay, so where does theta over 2 live? 0 to 2 pi. So I just divide everything by 2 and we get that new domain. So I'm going to call that my beta. And so I'm going to set up an equation in terms of beta, and then just solve in terms of beta. So square root of 3 tangent of beta minus 1 equals 0. Okay, so if I move everything over, what does the tangent of beta equal? Good, square root 3 over 3. I'm going to go ahead and write it as 1 over square root 3 for just a second, which is actually equal to square root 3 over 3. Okay, but the point being, where is tangent positive? First and third. Okay, so I'm looking for the angle that when I do sine over cosine, I end up getting a 1/2 there and a square root 3 over 2 there. So when I take sine divided by cosine, I get 1 over square root 3. Hey, which angle is this? Pi 6th. We've been dealing with that one all class. Seems like, right. Well, that's good. So in the first, it's pi over 6. What is it in the third? 7 pi 6. Okay, so beta, come back over here, is pi over 6 or 7 pi over 6. Okay, now I did not start this adventure to solve for beta though. I started it to solve for theta. So theta over 2 equals pi over 6. We'll kind of work out the math on what we do with the 2, and then we'll see how that's going to modify our answer. Okay, so what do I do with the 2? Multiply both sides by 2. Okay, so I get theta equals, what does theta equal now? Pi thirds. Okay, so same logic with the 7 pi 6. So if I multiply by 2, what do I get for my angle? Seven pi over 3. Okay, in other words, this time when we're multiplying by 2, we get 7 pi thirds. Okay, now, kind of go back up and look at our question. It says find general, so we'll go back and we'll talk about the general case here. But what about 0 to 4 pi? Did I find all of my solutions between 0 and 4 pi? What would 4 pi look like in terms of thirds? 12 pi over 3? Okay. So now we got to think for a second. Is 7 pi thirds the biggest, or can I go one more? Like how do we go from pi to 7 pi? We added 6 pi, right, to the numerator. So if I add 6 pi to 7 pi, where would I be? 13. Is 13 bigger than 12 pi thirds? Okay, so are my two angles the only two between 0 and 4 pi? Here's 4 pi, which is 12 pi thirds. Here is 7 pi thirds. Is 4 pi bigger than 7 pi thirds? Yes. Here is 13 pi thirds. So did I get all the angles between 0 and 4 pi that satisfy this equation? Yeah, yes, right. How do I know? Because the next angle up from 7 pi thirds is bigger than 4 pi. How did I know how many to count up? Well, the nice part about doing this modified approach of doing an angle substitution like we did, you're always going to get, your answers are always going to be within the required domain. So because they told me 0 to 4 pi and I did a substitution based off of that, then when I get done solving, my answers, how many I have, are going to be between the 0 to 4 pi. Won't be anything else past it if I do the substitution approach. Okay. Now that still leaves us the k case, the general case. So coming back up here, let's kind of think about why it works this way. So think about our angle. I got pi 6 and 7 pi 6. Well, what do I have to do to get the next answer? Like, is it all going to be based off pi 6? Or is it some going to be based off pi 6 and some going to be based on 7 pi 6? What do you think? Do I have to add 2 pi every time to get the next angle that satisfies this? Or can I get away with adding something else? Yeah, what if I add pi? If I add pi over 6 plus pi, I get 7 pi over 6. And if I add pi to 7 pi over 6, I get the next form of this. And if I add pi to that, I get the next. So in other words, adding pi is going to get the job done. So looking at our answers, if I take pi thirds and I add k pi, right, that should generate the next angle in my pattern. So in other words, I don't need 2 pi this time, I need just k pi. Okay. Why is this different though? How come last time I had 2, let me kind of scroll back up for a second. So last time when I looked at the general case, I had to have 2 different forms. One was based off pi 18 and one was based off 5 pi over 18. How come this one is just based off pi thirds? Okay, that's part of it. But what's different about this question that makes this so weird? Like, why is it not 2 pi? Why is it just pi? Okay, yeah, notice the trig function we went with. The trig function is tangent. Tangent repeats itself every pi, right? We think about the tangent graph. It does the same pattern every pi units. So it makes sense then that if I look at the infinite case, I'd only have to add k pi instead of just 2 pi. Okay. All right. You're going to be sad for me to say this, but this is our last trig equation. I know, so sad. You're like, what's coming up next? Any question on this? Yes.
Why weren't there more answers than the other one that had like 4 or 6?
Okay. How many times around the unit circle did I have to go? So I went around less, which is part of the reason why it's less. The other part is this one had me solve for the half angle. So if you think about it, in a unit circle, where's tangent positive? It's positive 2 places. But if I'm only looking at half of the unit circle, where is it positive? It's only positive once. Okay. If I go up to the previous example, there's sine. Well, how many places is sine positive in one unit circle? 2, but I went how many times around the unit circle? 3 times, so 3 times 2 is 6. So there should be 6 answers for this question, whereas this question I only have 2 answers because I only went around, we went around actually twice, or once around the whole unit circle. Does that make sense why there's less answers? So there's less answers because the angle we solve for is different. So you don't want to memorize this with, there's going to be 6 answers. I got to hunt for 6 until I find them. You don't want to learn it that way. You want to look at what are you doing, what are you replacing, what's the substitution, and what is the domain of that substitution. In other words, how many times around the unit circle should you go and base your answer around that? Okay? All right, anything else on this? No?